Suppose Neil Armstrong threw a golf pause. Hopefully, you know who Neil Armstrong is. If you don't, you need to look it up. Spoiler alert, has to do with the moon. Something else. Don't mess with Buzz Aldrin. He'll punch you in the face. Yeah, look that up too. Neil Armstrong threw a golf ball into the air while he was standing on the moon. The height of the golf ball was modeled by the following equation, where S is measured in feet and T is measured in seconds. So we got our time is in seconds. This S of T, the whole function is describing the golf ball's height that my boy Neil threw up into the air on the moon. Find, or lack thereof, find the average rate of change of the golf ball between 5 and 7 seconds. We've been doing this fairly regularly now. So I'm going to take S of 7 minus S of 5, and then my time interval down here. What's this thing called up here? If this is time interval, what's this? Displacement, correct answer. So punch that in your card. So you punch 7, all that, minus, throw 5 in, all that. Make sure you put parentheses around it if you usually calculate that kind of stuff. And you will get negative 5.74 feet per second. I think it's in feet. It says seconds. We'll say it's feet. All right, we okay with that? Let's find the instantaneous over here. So we got the same problem, same graph, same everything. Approximate the instantaneous rate of change, that's the velocity, of the golf ball at 7 seconds. So previously we said if we're going to estimate the instantaneous velocity or instantaneous rate of change, we're just going to make our time interval really, really small, close to that number. Okay, so what I'm going to do is I'm going to say S of 7.0001 minus S of 7 all over 7.001 minus 7. So that's two numbers, one of them 7. This number is really, really, really close to 7. So the average rate of change that is really, really close to 7 will give me a good estimate for the instantaneous rate of change. So I'm going to take 7.0001 and I'm going to punch it in my calculator. Spoiler alert, if you've got, or maybe pro tip here, if you punch this into your calculator, then go back and then just make it 7.0000. That'll make it a little bit easier. You don't have to keep punching your calculator. Punch all that in, and you get negative 11.18 feet per second. What does that mean? That means that it's coming on the way back down. Okay, golf ball's been thrown up. It's coming on the way back down. You could graph that on Desmos and look at it on Desmos and see that it's on the way back down. Let's look at the next one. A pendulum swings from the ceiling. Its distance, because people just have pendulums hanging from their ceilings. You know who has that? Ms. J, Ms. Johnson. What a weirdo. Lives in Pendergrass. It's distance D in feet. Sorry, JJ, you have to live with that all the time. Sorry. It's distance D in feet from one wall of the room depends on the number of seconds T since it was set in motion. Okay, so this function, this D of T, is the feet from one wall in T seconds. So think about the pendulum, it's going to go back and forth, back and forth. That's the cosine function, okay? So cosine function, you know, where does cosine start at, people? In the clouds. So proud of you, Liz Marr. Great job. You knew in the clouds. All right, so we got this. Assume that the following is an equation for D as a function of T. So that's the time, that's the distance from the wall. So it's going to be getting close to the wall, then it's going further away from the wall, getting close to the wall, further away, from that kind of stuff, okay? You want to find out how fast the pendulum is moving at a given T, and whether it is approaching or going away from the wall. This word is instant, at a given instant T. And whether it is approaching or going away from the wall. Find D, so find the distance when time equals 4. What mode should your calculator be in? Well, it should be in radian mode. Okay, put it in radian mode. Find D when t equals 4. That's just plugging it in. That's not anything special. D of 4, that would be 20 plus 16 times cosine of pi over 3 times 4. And when you punch that in your calculator, you get 12 feet. Okay, so that's the distance at 4 seconds, how far it is away from the wall. Okay, all right, let's look at the next one. So we still have the same function, and we're looking for an estimate of an instantaneous rate of change at t equals 2.5. So at t equals 2.5. So instantaneous rate of change, same kind of deals up here with my boy Neil and his golf ball on the moon. We got to choose two numbers that are really, really close together to estimate the instantaneous rate of change. So I'm going to write it like this. Let's write instantaneous rate of change. And I'm just going to choose like 2.5, and I'm going to throw some zeros and a 1 on there. So d of 2.5001 minus d of 2.5 all over the time interval. So you'd have to punch 2.5001 into that function, get an answer, and then subtract. When you punch 2.5 in right there, get an answer. Divide by all this stuff, and you would get negative 8.376 feet per second. Okay, at that time, so we're still at 2.5 seconds. At that time, is the pendulum approaching the wall or moving away from it? And explain. Well, we got a negative number. What does that mean? Well, negative 8.376%. So, like, remember up here? Like, that golf ball is getting closer to the ground. Okay, coming down, it's getting closer to the ground. Right here, negative number. It's getting closer to the wall because we're decreasing here. So let's just write something like that. The negative number, hashtag, means distance to wall is decreasing. Okay, so we can write, therefore, it's approaching the wall. Next one. An initial deposit of $500 in your bank will things I don't want to talk about right now. That retirement account. Sheesh. Ouch. Anyways. Oof, man, that's rough. An initial deposit of $500 in your bank will have a balance after T years, given the following equation. Okay, so after T years, we'll have this amount. And you've done this before with the interest and all that kind of stuff in Algebra 2, I think, maybe in Algebra 1. What are the units of rate of change of this function? That's just the rate of change. So you're going to have like dollars per however many years you plug in. So let's put it as dollars per year. Okay. Find the average rate of change over 0 to 1 year. So after the first year. Well, let's do this. Okay. P of 1 minus P of 0. Time interval on the bottom. I'm going to plug 1 into my calculator right there. Subtract when I plug in 0 right there. 0, that would be 1, so that would be 500. And so you get $30 per year. is your average rate of change over that first year. Okay, so let's estimate the instantaneous rate of change when t equals 1. So we did the average rate of change between 0 and 1. Let's estimate the instantaneous rate of change at t equals 1. So let's just choose two numbers right there next to each other. And one of them's going to be 1. So I'm going to do like 0.99999. I don't know how many nines I just said. I'm going to do like 3 or 4 of them. So let's do p of 1 minus p of 0. Let's do 4 of them. Why not? Okay. So I am doing an average rate of change for numbers really, really close to this number. Therefore, we're going to be a good estimate for the instantaneous rate of change. When I punch that into my calculator, I get $30.88 per year.